All right, as I ran short of time on the other video, I just wanted to go back to this one saying that we have, as we know, 75 newtons of force of frictional force. So we write force of friction between the ground and the bike. And because it's that constant speed, I know I need to have a normal pushing force from the person who's pushing on the bike with his foot of 75 newtons. So this here is, again, a balanced force diagram. And it has a 0 force, 0 newtons as net force. Okay, so let's move on to the next problem. In the next problem, you have a couple dining in an Amtrak car heading towards Sacramento. The car is again traveling at a constant speed of 95 miles per hour. So constant speed means that you need a balanced force diagram. So that's something we know. The train's engine is exerting a forward force. I think that mentions it in your handout of 150,000 newtons. That means that it is pushing. Again, we know that that's a normal force of 150,000 newtons. And that's an interaction between the engine and the train. The other things that we need to know is here I have my train. Let's see what other forces are involved. Again, we have the earth over here. Let's change colors and pens. And so I know that I have a gravitational pull between the train and the earth. I also know that the train's wheels are on the track, so it's touching the track. Again, I'm always asking myself what's touching the train. I'm going to say this is a normal force because the tracks are pushing the train up. All right, so we have a gravitational force pulling the train down, the normal force pushing the train up. I also was just told I have a normal force of 150,000 newtons pushing that train forward. Because it's moving at a constant speed, I also know that I need to have a frictional force. So that frictional force is between the wheels and the track, and it's going to go the opposite direction of this pushing force. So let's see what that force diagram is going to look like. So we'll start off with our point. The activity says that we have a gravitational force of the train of 75,000 newtons, and this is a gravitational force between the earth and the train. I also know I have that normal force, so that should be a vector that's equal. It doesn't look quite equal, but my apologies. This is a normal force between the tracks and the train. Let's call them the rail. I'll make that an R, and the train. And that is going to have to be equal to the gravitational force of 75,000 newtons. I also was told I have a normal force pushing the train forward of 150,000 newtons. This is my normal force between the engine and the train. Okay, it's pushing that forward. And because I know it's a balanced force diagram, this does not look balanced. I need to create a vector that's of equal length to this one. That is a frictional force between the track, the rails, and the train. So this vector will equal this. These two vectors will equal these each other. This value is going to be 150,000 newtons. And there's your force diagram. Again, you have 0 newtons as your net force. All right, moving on to the last one. You have a guinea pig sitting on a skateboard, and it's again traveling a constant 3 miles per hour. Because it's constant, I know it has to be balanced, okay? Always that constant speed. I know that the guinea pig weighs 5 newtons, as well as the skateboard that weighs 5 newtons. And not only that, but it has a pushing force of 10 newtons. Okay, so here's my guinea pig. Let's put the ground over here and the earth over here. I'll change my pens to green just so it's easier to see. So the first interaction I know always is that the skateboard is feeling the force of gravity due to the earth. And then the next question is, and that's going to be a downward pull. So my next question is, well, what is touching my skateboard? So definitely the guinea pig is touching my skateboard. What is the guinea pig doing to the skateboard? It's actually pushing it down. It's pushing down on it, and that push force, remember, is a normal force. Okay? How about for the ground? The ground is touching the skateboard as well, and that ground is again pushing it up. So the ground is pushing it up, so I have a normal force pushing up. I told you also that you have a force, looks like it's a forward force of 10 newtons because the rear foot is pushing it, so that's my normal force. So I have this guinea pig pushing, and that normal force, I'll write as just normal. Pushing that skateboard forward. Because it has to be balanced, I know I need to have a frictional force, and this frictional force is between the tire of the skateboard and the ground. So let's create that into a force diagram. Frictional force, of course, is this direction. So I have my point of reference. Gravitational force is Fg between the earth and the guinea pig. It looks like the guinea pig has 5 newtons of force. Then I should create an even longer vector. My apologies that it isn't longer. Excuse me. Let me restate that yet again. We're having a reference point being the skateboard. So this force of gravity is between the earth and the skateboard. That's 10 newtons, so this one should be a smaller one. Then I have a normal force pointing down between the guinea pig and the skateboard, and that's 5 newtons. So the upward force, because it has to be balanced, that the ground is exerting onto the skateboard is considered a normal force. And that's going to be the sum of these here. We have 10 newtons and 5 newtons. That works out to be 15 newtons. All right, normal force, we said, was between the guinea pig and the skateboard. That is 10 newtons. And then in order to have this be balanced, I need to have a frictional force of 10 newtons between the skateboard and the ground. So the ground and the skateboard. And that creates our balanced force diagram.